Okay, question 14. We went on to understanding that these long polynomial equations or expressions can sometimes be written in nice factored form, which the idea behind that is it literally helps with graphing and understanding the behavior when you graph the polynomials. And so the first step here is to recognize that when we have polynomials multiplied together, the result is a polynomial. And so these little factors are each of themselves little polynomials, and so we have this big polynomial that would result if we went ahead and multiplied everything out. This question is about finding the degree and leading coefficient of these polynomials in factored form. Remembering the reason we'd want to do that is because the degree and the leading coefficient tells us the end behavior of that graph, if you remember back from a couple questions. And so that's the goal and why we're doing this here. So to find the degree, we just really have to count up all the different powers of x's that are occurring here. So this little polynomial x cubed here has a power of 1, and it's getting cubed. So if we were to multiply this whole thing out, the first term we'd get 3 degrees from this term. Here this is a degree of 1, but it's being squared, so we'd get 2 degrees from that term. This one is also a degree of 1, but we're squaring it. We'd get 2 degrees from that term. And then when you're multiplying things out, we would add those different exponents to get a degree of 7 for this one. I'll come back to the leading coefficient. I just want to do a few more of these degree ones here. So here we have a polynomial of degree 1, but we're squaring it, so that would give us 2 degrees. This polynomial is a degree of 1, but we're just raising it to the first power. That would give us 1. Here we have a first power, but we're just raising it to the first power to 1. So the degree of this expression, if multiplied out, would be 4. For the next one, we have a degree of 1, but it's raised to the 10th power, so 1 to the 10th power. That would give us 10 degrees from that term. Here we have this is a first degree polynomial, but we are raising it to the 10th power. So that's going to give us 10 degrees. If we add those together, this would be, a big polynomial, but it would be a 20th degree polynomial. Hopefully you're getting the pattern now here. These are all degree 1. All these powers are just raised to the first power, so this would give us a 3rd degree polynomial, or a cubic. And this one contributes 4 degrees. This is a 1st degree, but it's raised to the 4th power, and that would give us a degree of 8. So this would give us a piece of the end behavior, but then we essentially need to understand if that leading coefficient is negative or positive. So what we're going to do is look at all those leading coefficients and multiply them together. So this first one has a leading coefficient of 1, and we're cubing it, so that's 1 cubed. This polynomial has a leading coefficient of 1, and we're squaring it. So that would be 1 squared. This polynomial here has a leading coefficient of 1, and we're squaring it. So if we were to multiply all those leading coefficients out, we would get 1 cubed times 1 squared times 1 squared. Well, that's just going to be 1. Here, leading coefficient is 1, and we're squaring it. This leading coefficient is 1, and we're not squaring it. This leading coefficient is 2, and we're not squaring it. And then we have to worry about this negative sign out front. So all those things are going to be multiplied by a negative 1, or whatever that number would be out in front. And so 1 squared times 1 times 2 is negative 2 would be the leading coefficient here. Here the leading coefficient is 1, and we're raising it to the 10th power, so we get 10 of those. Here the leading coefficient is 1, and we're getting 10 of those. So 1 times 1. 1 to the 10th times 1 to the 10th is still 1. Here the leading coefficient is 1, and we're not squaring it or anything. This leading coefficient is 1. The leading coefficient of this polynomial is 1. We also have this 3 out front, which is itself a polynomial, so that's 3. So the leading coefficient of this guy would be 3. And then here hopefully you just see that this is 1 to the 4th, 1 raised to the 4th power, that's 1 to the 8th, so the leading coefficient here is also 1. So now, knowing that we have the degree and the leading coefficient, we could sketch the end behavior of these graphs. Just as an example, for f of x here, we know it's an odd degree, so it's going to look like a disco. And then the leading coefficient is positive, so it's not reflected. So this would be the end behavior of that one. And let's take a look at this next one just for fun too. So here the degree is 4, so the arms go in the same direction. That would be x to the 4th. But we see that the leading coefficient is -2, so that's going to reverse them and reflect them. So it's going to come down like this, and that would not. And so the end behavior would be facing down in both cases. So 15. So we have polynomials in factored form again. In fact, they're the same ones. And the idea here is to determine what the zeros are, which means where they cross the x-axis. And then the multiplicity of each root, which is kind of how many times that root appears in the equation. And you may recall, and we'll talk about it soon, that that multiplicity tells you what happens to the graph at that root. So I'm just going to go through one of these in detail, and then hopefully you'll get the rest from the answer key. So to get the roots, we have to set this polynomial equal to 0. That's what it means to find the roots. And then to find the roots, it's going to set all the, if a bunch of things multiply together equals 0, that means at least one of them has to equal 0. So if we did that here, we'd have to have x equals 0, or x minus 2 equals 0, or x minus 1 equals 0. And if we solve these, that's x equals 0, this is x equals 2, this is x equals 1. So those are going to be the zeros of this polynomial. It'll cross the x, or touch the x-axis, I should say, at these points, 0, 2, and 1. Now we have to understand what this idea of multiplicity means. It's essentially how many times that solution appears in the equation. So here, x equals 0, well, that actually happened 3 times. If we wrote this out, we'd have x equals 0, or x equals 0, or x equals 0 3 times. So that's going to have a multiplicity of 3. Essentially, it's this power on the factor that's going to be what the multiplicity is. X minus 2 appeared twice in our solution if we would have written it all out. X minus 2 equals 0, or x minus 2 equals 0. So that 2 is going to give us a multiplicity of 2 here. This guy is going to give us a multiplicity of 2 for that 0. And so that's all this is. This problem is just asking you to find those two things, because again, we're going to see that those two things are important for graphing. Here maybe I'll do one more in a little bit of detail. Set that equal to 0, or set this one equal to 0, or set that equal to 0. 2x minus 1, so that's a little different looking factor. And solve these little guys here. X equals 1, x equals 2. Here, if I add the 1 to both sides, I get 2x equals 1, or x equals 1/2. So those are my zeros. Go ahead and write those over here. 1, 2, 1/2. And the multiplicity of those zeros are how many times they appear in the factored form. Well, that x minus 1 appeared twice. X minus 2 appeared once, 2x minus 1 appeared once. And then here you can check the answer key for these guys, but hopefully those two gave you enough for how to go about doing this.